Every March and September, a massive, highly predictable wave of heavy rain sweeps across Lake Victoria and the Ugandan landscape. It arrives like clockwork. But if you talk to someone living in Europe, their year looks very different, defined by freezing, snowy winters, followed by hot, dry summers. Why does the equator miss out on these drastic temperature shifts entirely, yet receive such immense, predictable rainstorms twice a year? To find the answer, we have to pull back from the local storm clouds and look at the planet from space. The local weather outside your window right now is dictated by two massive, continuous planetary movements. The first movement is rotation. The Earth spins on an invisible axis from west to east, taking exactly 24 hours to complete one full turn. Because the planet is a sphere, the sun only illuminates one half of it at any given time. As we spin into the light, we experience day, and as we spin into the shadow, we experience night. To track this spinning motion, humans drew an imaginary grid over the planet. We call the lines running from the North Pole down to the South Pole lines of longitude. The starting point for this grid is the prime meridian, or 0 degrees, a line that passes directly through the Royal Observatory in London. The time on your clock is a mathematical result of exactly where you sit on this longitudinal grid. This timeline graphic shows how we track time based on the Earth's rotation. The planet spins through 360 degrees every 24 hours, which means it covers exactly 15 degrees every hour. Let's trace the distance from that 0-degree line in London over to Kampala, which sits at 45 degrees east longitude. If we divide that distance of 45 degrees by the 15-degree hourly rate, we get a precise 3-hour time difference. Because Kampala is positioned to the east of London, it rotates into the sun's light first. We add those 3 hours to the clock. If a clock strikes 12 noon in London, it is exactly 3 p.m. on the bustling streets of Kampala. Knowing someone's longitude gives you the geographic mathematical power to calculate the exact time they are experiencing before you ever call them. The second planetary movement is revolution. While the Earth is spinning, it is also traveling in a massive orbital path around the Sun. This journey takes exactly 365.25 days. This model shows the Sun in the center and the Earth orbiting it. The Earth does not sit straight up and down in space. Its axis leans permanently at a 23.5-degree angle. When the Earth reaches the part of its orbit where the northern hemisphere is tilted toward the intense heat of the sun, Europe experiences summer. 6 months later, the planet reaches the opposite side of the sun. The northern hemisphere leans away into the shadows, triggering the cold temperatures of winter. This permanent 23.5-degree tilt, combined with the yearly orbit, is the reason different parts of the world experience drastic, predictable temperature changes. This brings us back to Uganda, sitting precisely at 0 degrees latitude on the equator. Because the middle of the planet never leans extremely far away from the sun or intensely toward it, it receives consistent light all year. This avoids snowy winters entirely. Twice a year, in March and September, the Earth's orbital position aligns perfectly so the sun passes directly overhead at the equator. We call this the equinox. This direct, intense heat rapidly warms large bodies of water like Lake Victoria. The moisture is driven upward into the atmosphere, creating heavy rain. Uganda's predictable rains occur because the equator physically crosses the sun's most intense, direct path twice every year. The rain outside your window represents the movement of a tilted planet traveling millions of miles through space. The time difference between cities is a strict mathematical measurement of our planet spinning from west to east. By understanding these two planetary movements, you now hold the geographic power to calculate the time and predict the seasons for anyone, anywhere. This knowledge transforms the ground beneath our feet into an incredible, mathematically predictable moving spaceship.